We have seen that a spanning tree of a connected graph G is a subgraph T that includes all vertices of G and some or all edges of G such that all vertices are connected and there are no cycles. For example, for this graph G, these all are spanning trees. These are the weights of these spanning trees. These weights are the sum of weights of edges included in the tree. For example, for this tree, weight is equal to 6 plus 3 plus 4 equal to 13. Now, a minimum spanning tree of graph G is a spanning tree whose weight is minimum among all the spanning trees of G. For example, for this graph, this is the minimum spanning tree as its weight is minimum. If the graph contains some edges with equal weights, then more than one minimum spanning trees are possible. While if all the edges of the graph have unique weights, then there will be only one minimum spanning tree for the graph. Now, finding minimum spanning tree can be useful as it gives us the most economical way of connecting all the vertices of a graph. In this course, we'll learn about these two algorithms for finding minimum spanning tree of a graph. Both of these algorithms use the greedy approach. In this video, we'll learn about Prim's algorithm, which is used for creating a minimum spanning tree. The procedure of Prim's algorithm is somewhat like that of Dijkstra's algorithm. We'll give each vertex a status. If a vertex is temporary, it means that it has not been included in the spanning tree. And if a vertex is permanent, it means that it has been included in the spanning tree. Initially, all vertices will be temporary, and at each step of the algorithm, we'll make a temporary vertex permanent. And the process stops when all the vertices become permanent. That is, when all the vertices are included in the spanning tree. Each vertex is given two values, length and predecessor. Length of a vertex represents weight of the shortest edge connecting the vertex to a permanent vertex, and predecessor represents that permanent vertex. Now, when the algorithm starts, the length of all vertices is initialized to infinity, which is a very large number, and predecessor is initialized to nil, which is taken as -1, since our vertices start from 0. Now, a temporary vertex can be relabeled, that is, its length and predecessor values can be changed, but once a vertex is made permanent, it can't be relabeled. For making a vertex permanent in each step, the greedy approach is used. The vertex which has minimum length is made permanent. Now let's see the whole stepwise procedure of the algorithm. Initially, for all the vertices, length is equal to infinity, predecessor is nil, and status is temporary. We will select any vertex of the graph as root vertex and make its length equal to 0. Now, from all the temporary vertices of the graph, we'll select the temporary vertex that has minimum length, and we'll make it permanent, and now it becomes the current vertex. At the start of the algorithm, root vertex has minimum length, so root vertex will be the first one to become permanent. Now, in second step, we'll examine all the temporary vertices adjacent to the current vertex and relabel them if required. Now let's see what's the condition in which we need to relabel any vertex adjacent to current vertex. Suppose V is a temporary vertex adjacent to the current vertex that we are examining. If weight of this edge is less than length of V, then length of V becomes equal to weight of this edge and current becomes predecessor of V. Otherwise, no relabeling is required. Now these steps 1 and 2 are repeated till either there are no temporary vertices left or all the temporary vertices that are left have length equal to infinity. If the graph is connected, then all vertices of the graph will become permanent at the end of the algorithm. If the graph is not connected, then vertices which are not reachable from the root vertex will remain temporary with path length infinity. In this case, there is no spanning tree possible for the graph. Now in the next video, we'll understand the whole procedure with the help of an example. In this video, we'll understand the procedure of Prim's algorithm with the help of this graph. Initially, all vertices are temporary. Length of all vertices is infinity and predecessor is nil. We'll take vertex 0 as the root vertex. Now the first step is to make length of root vertex 0. So we'll make length of this vertex 0 equal to 0. Now from all the temporary vertices, we have to select the temporary vertex with minimum length. This is the vertex with minimum length. So we'll make it permanent. And now this is a current vertex. So we'll examine all temporary vertices adjacent to this vertex 0. First we take this vertex 1. This 19 is less than infinity. So we'll relabel it. Next we take this vertex 3. This 14 is less than infinity. So we'll relabel it. Next we take this vertex 4. This 12 is less than infinity. So we'll relabel this also. Now from all the temporary vertices, this vertex 4 has the minimum value of length. So we'll make it permanent. Now predecessor of 4 is 0. So this edge 0, 4 is included in the minimum spanning tree. Now 4 is a current vertex. So we'll examine all temporary vertices adjacent to this vertex 4. First we take this vertex 1. This 18 is less than 19. So we'll relabel it. Next we take this vertex 2. This 17 is less than infinity. So we'll relabel it. Next we take this vertex 3. This 13 is less than 14. So we'll relabel this vertex 3. Next we take this vertex 5. This 16 is less than infinity. So we'll relabel this vertex 5. Next we take this vertex 6. This 21 is less than infinity. So we'll relabel this vertex 6. Next we take this vertex 7. This 22 is less than infinity. So we'll relabel this vertex 7. Next we take this vertex 8. This 24 is less than infinity. So we'll relabel this vertex 8 also. Now from all the temporary vertices, this vertex 3 has the minimum value of length. So we'll make it permanent. Now predecessor of 3 is vertex 4. So this edge 4, 3 is included in the minimum spanning tree. Now vertex 3 is a current vertex. So now we'll examine this vertex 6, which is adjacent to 3 and is temporary. Now 28 is greater than 21. So we'll not relabel this vertex 6. Now from all the temporary vertices, this vertex 5 has a minimum value of length. So we'll make it permanent. Now predecessor of 5 is 4. So this edge 4, 5 is included in the minimum spanning tree. And now this vertex 5 is a current vertex. So we'll examine these vertices 2, 8 and 9, which are adjacent to vertex 5 and are temporary. First we take this vertex 2. This 15 is less than 17. So we'll relabel this vertex 2. Next we take this vertex 8. This 26 is greater than 24. So we'll not relabel this vertex 8. Next we take this vertex 9. This 27 is less than infinity. So we'll relabel this vertex 9. Now from all the temporary vertices, this vertex 2 has a minimum value of length. So we'll make vertex 2 permanent. And now this vertex 2 is a current vertex. So we'll examine these vertices 1 and 9, which are adjacent to vertex 2 and are temporary. First we take this vertex 1. This 20 is greater than 18. So we'll not relabel this vertex 1. Next we take this vertex 9. This 29 is greater than 27. So we'll not relabel this vertex 9. Now from all the temporary vertices left, we have this vertex 1, which is minimum value of length. So we'll make this vertex 1 permanent. Now this vertex 1 is our current vertex. Now there is no temporary vertex that is adjacent to this vertex 1. So now from all the temporary vertices left, we have this vertex 6, which has minimum value of length. So we'll make vertex 6 permanent. Now 6 is our current vertex, and this vertex 7 is adjacent to 6 and is temporary. So we'll examine this vertex 7. This 23 is greater than 22. So we'll not relabel this vertex 7. Now from these 3 temporary vertices left, this vertex 7 has the minimum value of length. So we'll make it permanent, and now this vertex 7 is our current vertex. And we'll examine this vertex 8, which is adjacent to this vertex 7 and is temporary. Now this 30 is greater than 24. So we'll not relabel this vertex 8. Now we have these 2 temporary vertices left, and this vertex 8 has a minimum value of length. So we'll make this vertex 8 permanent. Now this 8 is our current vertex, and we'll examine this vertex 9, which is adjacent to vertex 8 and is temporary. Now this 35 is greater than 27. So we'll not relabel this vertex 9. Now this is the only vertex that is temporary. So we'll make it permanent. Now all the vertices are permanent, and we've got a minimum spanning tree.